now we can plot the. Excuse me. So we can plot the salinity difference between summer and winter. So salinity difference at the upper layer here, it's 2.5 sigma units. That's the salinity unit. So that's the range of salinity that the brine experiences between summer and winter. We can do the same with temperature. So that's 12 degrees between summer and winter. Okay? So that's the thermohaline evolution of the brine between winter and summer. It gets warmer and saltier. When we look at the slope of this curve, so that's the dependency of saturation on temperature. So it has some slope, and when the temperature changes in 12 degrees between summer and winter, the salinity and saturation changes in 2.5 sigma units. So it's more or less parallel to the thermohaline evolution of the brine, and that's causes caused a challenge in determining halide saturation in the brine. So what will be the trajectory of this brine with respect to this solubility curve? It will determine whether the brine is supersaturated or undersaturated with respect to halide. And we will ask when halide will precipitate during the dry summer or during the cool winter. That is not clear. Additionally, we can add this depth variation. So the Dead Sea experienced the thermohaline stratification. These are depth profile of temperature. So temperature is uniform during the winter, and we have a thermal stratification during the summer. And the black crosses are salinity measurements. So salinity is also uniform during the winter, and we have salinity stratification during the summer. So we have an upper layer which is warmer and more saline than the lower one during the summer, with a thermocline at the depth, average depth of 25 meters, which considered to be a virtual bottom. And we can do the same for this depth variation with this TS diagram. So on the TS diagram, we plot the conditions at the part of the water column and the upper part of the water column. And again, they lie along this solubility curve. And now the question is, where will I precipitate? At the upper part of the water column and the lower part of the water column? This is a question. And another question is regarding the relations between these layers. This thermocline is considered to be a virtual bottom, but the question is, the thermocline really acts as a virtual bottom, meaning that there is no fluxes or no connections between the layers during the summer. And on the background of this questions, the objectives of the study will be to characterize spatiotemporal variations of water column properties and then to relate them to halide deposition. So we start by characterizing temperature and salinity along the water column. We use a standard oceanographic tool. So these are Ballon-Niskins for brine sampling, and this is the CTD for temperature profiling. That's what we use. And in the lab, we have an highly accurate density method that can capture the slight variations in salinity between different depth along the water column and between the seasons. And then we're interested in the degree of halide saturation based on these measurements and halide crystallization rates along the water column. These are measured along these steel cables submerged along the water column from the surface water to a depth of 50 meters. And finally, we are highly interested in the textures of halide and the distribution of halide on the lake. So that's what's preserved in the geological record, and we want to relate it to the environmental forcing. So we will start from a simple observation. We will follow this cable, and after 30 days underwater, so during the summer, the water column is stratified. We deploy this cable, halide is crystallizing, and we want to measure the rate of halide crystallization along these cables. So the IES salinities during the summer are here, at the upper part of the cable. That's where we expect most of halide crystallization. That's it in this movie. So that's our cable on the water. We follow it down the water column, and here it is black. It means that it has no halide on the cable during the summer, after 30 days, although salinities in this brine are very high, meaning that the brine here is undersaturated with respect to halide. As we go down, suddenly this cable becomes white, meaning that halide is crystallizing from some depth along the water column, meaning that the brine here is supersaturated. So that was the cable submerged along the water column, and now in the day field, we come to we come with this boat and recover the cable, and the purpose is to measure the thickness of halide around this cable as the cable goes out of the water. By that, we measure the profile of halide crystallization rates along the water column. So that's the setup of the cable. The upper brine is saltier and warmer, but overall undersaturated. That's the indication from this cable. And below the thermocline, the brine has low salinity, but it's colder. And overall, it is supersaturated, as you see here. And these observations agree with observations from the lake floor. So that's the shallow lake floor and the corresponding depth. So no halide here, and massive halide cover in the deep part of the lake floor, and it matches to these photographs of the cable. So we have evaporation from the water surface. We have salinity that increases here at the upper layer, but halide is crystallizing only below the thermocline. So what is happening here? This raises a fundamental question. Something should supply salt for maintaining halide saturation below the thermocline. So what is the source of salt for halide crystallization? Here, below the thermocline. And if you want to complete this framework, so this is the cable during the winter, so after the same time interval, 1 month. During the winter, we measure much thicker halides around the cable on the upper and lower part of the cable. And by doing it systematically, month by month, come with a boat to the site of the cable and to cover it, we can measure profile of halide crystallization rates along the water column during more than 2 years. And by interpolating this data, we can build this contour diagram when the contours are halide crystallization rates. So darker contours mean higher crystallization rates. And we can clearly see that during the summer, halide is not crystallizing along the cable, like we see here, above the thermocline. We have low rates below the thermocline during the summer, and main halide crystallization occurs during the winter along the entire water column. So that was one objective of the study. Additional objective was to measure halide saturation. So usually, measurements of halide saturation are done by geochemical tools, but the problem in the Dead Sea is that the geochemical analyzers are not precise enough in order to capture the slight differences in salinity that we have in the Dead Sea. The natural signal of the salinity difference is about 1%, and that's more or less the precision of the geochemical analyzer. So we had to develop a new tool in order to measure halide saturation. So in the field we collect two brine samples. We brought them to the lab. We put them in an incubator shaker with an in situ temperature, and one of these tubes we add salt in excess. And the purpose is that after a few days, this brine will achieve equilibrium, and then we measure the salinity between the two brines, between the original brine and the equilibrated brine. So the difference in salinity between the brines will be our way to express halide saturation in the Dead Sea. So I will add these monthly measurements of halide saturation to these halide crystallization rates diagram, showing that we measure supersaturation during the winter, and under saturation during the summer, and these two independent methods agreed. So anytime that we measure supersaturation on brine samples, we had halide on the cable, and whenever we measure under saturation, we have no halide on the cable at the same depth. And as a reminder, this is the hydrological forcing. And you can clearly see that main halide crystallization occurring during the winter, which is considered to be the wet season. So the hydrological cycle is not dictating these variations in halide crystallization in the Dead Sea. So how can we explain it? By temperature variations. So this diagram, it's a depth and time diagram for the same time interval, showing the upper part of the waterline during the summer gets warmer, and that explains the under saturation here. And the cooling of the brine during the winter explains the high rates of halide crystallization along the entire water column. Okay, looking more carefully on this data, I will ask again, what is the source of salt for halide crystallization below the thermocline? Salinity is higher here, but halide is crystallizing here. And another observation will be this depletion in salinity for midsummer at the upper layer. So during the summer, as water evaporates, the salinity of the upper layer increases, but at some point in the middle of the summer, it starts to deplete, although evaporation continues. So something takes out salt from the upper layer during the summer. And these two observations suggest that there is